Hi, we're the Gear Changers robotics team based in the USA. Today we're here to talk about our robots and how we've developed them to perform the way they do on stage. I'm Alan, the main electrical person. This is Emin, our main mechanical person. And this is Solar, our main software person. For our start of the show, we have two dancing robots. These two dancing robots are identical robots that work together to make the magic happen. Our first main feature on our robot is the persistent turning of the drivetrain using a gyro. We chose it as a main feature because during our preparation for regional competitions, we struggled to have a reliable way of turning accurately and moving straight with our drivetrain. Our learning process with gyro and vector-based math, combined with the reliability we gain from our gyro sensor, makes this a first critical feature. We have to code a system to use data from a gyro and turn to an exact rotation.
So here we have our humanoid, and I've added some infrared sensors and I've connected it to this remote. And the whole idea is a remote will send a signal and tell this guy what to do. Now in the actual show, instead of this remote, I'm putting an IR emitter on the piano bot. And the piano bot's going to do the same thing as this remote. It's going to send a signal to this guy and it'll control what he's going to do. So just think of this as a piano bot. It's pretty much the same. So I'll start off with a 90-degree turn demonstration. We'll do that. As you can see, it did a perfectly 90-degree turn.
To go more in depth, let's start with the signal sent to the robots that start the show, the IR module. This is the sensor that Solar used to trigger the movement, and it's the same emitter that we use to start the show. The IR emitter will send a unique code by the form of a wavelength on the electromagnetic spectrum, and our robots will read that unique code and perform an action accordingly. Our gyro-based movement in the start is actuated by the MPU 6050 module. In our algorithm, we take the raw accelerometer values from the MPU module and create two vector objects based on the movement of our robots. Then interpolate an angle between the two vector objects, and once the robot moves to the desired angle, we stop the robot and the desired angle is achieved.
The movement commanded by the gyro sensor would not be possible without our second main feature, our servo-controlled wheel for controlled rotation in our robot. We selected this as a main feature because this mechanical feature solved a large issue: two wheels unable to move at the same speed when commanded by two different motors. The axle joining our motor solved this issue. Furthermore, as we modeled our drivetrain setup by rickshaw vehicles, we gained immense reliability with our movements. Here's our programmer Solar explaining more about this wheel.
One motorized wheel, and it's consisting of two motors that have the same axle, and then there's a big wheel or two mini wheels attached together, so they're forced to go at the same speed due to the same axle. Now on top we have a 60-kilogram servo, so by default it's straight, but it can rotate side to side. And now if we go a bit back, the cart will turn in a circle once the front wheel is rotated.
Going more in depth, the servo wheel is commanded to a specific rotation that we specify in code. The servo wheel uses a 60-kilogram servo along with two Rev Robotics DC motors controlled by an L290N motor driver. Much of our design process for our drivetrain started with creating something we call a minimum viable product. For our regional competition, we had a tank drive setup with a caster wheel in the back that was rotationally commanded based on time. As you can see in the video, even though we had a working drivetrain, moving straight was an issue. Adding our big servo wheel combined with the gyro-based movement resolved this issue and allow us to get precise movement for our drivetrain.
Now let's move into our third main feature, our dual directional capable arms. We chose this as a main feature because of the uniqueness and engagement that the arms bring. We also wanted to make the arms human-like. Our arms have a total of 3 servos, 2 are interconnected to allow for up and down and side-to-side movement, and 1 servo acts as an elbow to add another dimension of movement. Each servo is commanded based on rotation, and arm movements are made accordingly. One large issue we had with our arms was structural integrity. As seen in the video here, our arms consistently fell off as we had to prioritize weight during the construction of our arms. To rectify this, we added wooden reinforcements to our arms and switched from using wooden arms to foam arms, as foam proved to be a reliable material that was not only lightweight but offered the depth of design that we were looking for.
Our final main feature is our moving piano fingers. We chose this as a main feature because it demonstrates the versatility of our ability to play piano, and we believe that the piano playing is a critical part of our performance that adds step to the dancing done by the robots. Each of our fingers is a servo that actuates each piano key. The module of piano fingers is linked to a threaded rod actuated by a 24-volt DC motor. As this motor spins, the module moves accordingly. With our selected song, we only need to move in a 2-octave range. To control the movement of the servos, we use IR proximity sensors that command the motor to stop at different octaves as needed during our song. Our design for our threaded rod assembly was inspired by a similar setup used in 3D printers, and the servos were modeled similar to the hammer and strings found inside classical pianos.